Today we're going to talk about the simple pendulum. What is this simple pendulum? The simple pendulum consists of a point mass. This is the point mass, and suspended by a massless and unstretchable string. So let's consider this string as unstretchable. But of course, massless string does not mean it's really massless. We'll just neglect the mass of the string, because if we're going to compare the mass of the string to the mass of the bob, it's very, very, very small. Okay, so we'll just neglect it. Now, if the pendulum swings with a small amplitude, with vertical, okay, when you displace that bob at this angle, the very small angular displacement, then release it, then its motion is simple harmonic motion. It will swing back and forth. Okay, back and forth. So I have here is simple pendulum. So this pendulum is at rest, right? It's not yet disturbed. So it means this position here is the equilibrium position of the simple pendulum. Now if I'm going to displace at a certain angle from its equilibrium position and then release, look what happens. It oscillates, it moves back and forth, it swings back and forth, right? So can we say that this simple pendulum is obeying the simple harmonic motion, or is it moving in simple harmonic motion? Now, if the pendulum is moving in simple harmonic motion, so it means that there is force acting on the bob that tends the object return to its equilibrium position. So let us examine what are the forces acting on the bob, and let us examine why this simple pendulum really obeying or really in simple harmonic motion. Suppose I have here a pendulum. Okay, this is the equilibrium position of the pendulum, and the length of the string from the pivot to the center of the bob is L, right? And then this bob, the pendulum is displaced at an angle theta. Now let's consider this theta as very small angle, where the sine, tangent, the cosine of this angle, if this angle is very small, will be equal to the angle itself. If this angle is in radian. Now, if this angle is very small, then the arc moved by the bob will be approximately a straight line. Okay? If this is a very small angle, the arc is approximately a straight line. Right? So let us see what are the forces acting to the bob. Okay? First, the force of gravity, which is acting on the bob, which is always in downward position, and it's vertical to the Earth's surface, and that is what we call mg. Okay, the weight of the bob. The bob has mass, and it has a weight of mg. And what else? The string. The string is acting force to the bob. Okay, which is the tension. There's tension of the string, or the force acted by the string to the bob, which is at that direction, right? So I'll mark this as Ft. And then, if you can still remember, what is the free vector? We can move the vector anywhere in space, provided that the position and the magnitude is the same. So I will move this force Ft without changing its direction and its position and magnitude. So this is also Ft. So what will be the amount of tension of the string? So let us see later. Okay. Now, from the tip of weight of the object, making a line perpendicular to the tension of the string. Right. Now, if this is angle theta, and I will make a line parallel to the equilibrium position of the pendulum. So this is the transversal line. It cuts the two parallel lines. and then form equal angle. These two angles is the alternate interior angle, and these angles are equal. And this angle is opposite to this angle, and this is also theta. Alright? So the tension, as you can see, we form a right triangle. So meaning, the tension of the string is equivalent to the weight of the bulb cosine of the angular displacement theta. Right. Next, what is this? This line of the right triangle is opposite to the angle theta. So meaning this is mg sine theta. Pointing at that direction. So what force that is, what component of force that is pushing the bulb to the equilibrium position, or tends the object, or tends the bulb move or return to the equilibrium position? Mg sine theta. Okay, so there is force acting on the bulb that pushes it towards the equilibrium position. Okay, and that is what we call the restoring force. Fr is the restoring force, which is the mg sine theta. Alright, sine theta. Next, what is this sine theta? Now, for very small angle, arc can be considered as approximately line. Right? This arc is approximately line. So it means this is perpendicular to the string, length of the string. So sine of this angle, theta, is the opposite side, L. Okay, it's the hypotenuse side. So this is S. This is S, the arc, okay, which is opposite to angle theta. Now, if this is L, this is also L, since this is the length of the string, and this is also L. So the sine of this angle is S over L. S over L. Okay, so F of R here equals, I will replace sine theta by S over L. So this is mg S over L. Alright. So is this pendulum also obeys Hooke's law? Let us compare this equation to the Hooke's law. Hooke's law equation, which is F equals negative x or negative kx. The restoring force is negative kx. The restoring force is dependent on the position. How about this restoring force? Is this dependent on the restoring force? K here is the spring constant. So constant, it means it is true to every position. Now, comparing to Fr, which is equal to mg sin theta, or mg S over L, S is arc, L is the length of the string. Okay, so let us compare this. K is constant. What is constant? As the pendulum oscillates, there is no change of the acceleration due to gravity g, and also there's no change of mass. Mass is the same at every position. Acceleration due to gravity is the same at every position. At this position, at this position, at this position of the bulb. What else? The length of the string is constant at every position. So it's not changing as this pendulum oscillates. Okay? The length of the string at this position of the bulb is the same as the length of the string at this position of the bulb. So M, G, and L are constant like K. So K can be considered as mg over L. Okay, and X is the arc. The X is the arc S. I have here a pendulum. It is at the equilibrium position. It is at rest, initially at rest, and then I will disturb this, then displace at very small angle, and then release. Okay, it swings back and forth. Then it moves. What is the one cycle here? One cycle, if this is the positive amplitude, then this is the negative amplitude. Now, if the pendulum moves from A to negative A and then back to A, that is one cycle. And the time required to move one cycle is what we call period. If you can still remember, the period is the amount of time to move from A to negative A, then back to A. Okay. Now, if there is period, then there is frequency. An object that is moving in simple harmonic motion must have a frequency, an angular frequency. Now, if this pendulum acts or moves in simple harmonic motion, then there is frequency. Okay? So this is the amplitude, this position is the amplitude, and then this position here is negative amplitude. So this is also L. So this is the maximum displacement from equilibrium position, and also A is the maximum displacement from equilibrium position. So it moves an R, so there is angular frequency. Now, angular frequency for an object moving in simple harmonic motion, omega, okay, if you can still remember, omega is the square root of the spring constant, where an object attached to the spring and then oscillates and moves in simple harmonic motion. The angular frequency is the square root of its spring constant over the mass attached to the spring. Right. So let us substitute K by mg over L. What will be the angular frequency? That is mg over L over m. So we can cancel m here. So the angular frequency is g over square root of g over L. Okay? And then we know that the angular frequency is 2 times the 2 pi times the frequency. Okay? And then frequency is reciprocal to the period, or period is reciprocal to the frequency. Okay, so period will be, from this equation we can see that F is equal to angular frequency over 2 pi, or period equals 2 pi over angular frequency. And what is this angular frequency? That is the square root of the acceleration due to gravity over the length of the string. So period is 2 pi square root of L over G. So this is the period of the simple pendulum. Okay? So this is the period of simple pendulum, 2 pi square root of L over G. Where G here is the acceleration due to gravity, which is approximately, G here is approximately 9.8 meters per second squared, and L is the length of the string. Okay? So as you can see, the expression T equals 2 pi square root of L over G, okay, you cannot see variable mass. So meaning, the pendulum, the simple pendulum, is independent on the mass. Okay? The period of simple pendulum is independent on the mass, but it depends on the length of the string and the acceleration due to gravity. So that is the simple, this is the period of simple pendulum. So let us see if the period of simple harmonic motion is dependent or independent to the mass of the bulb. So if I'm going to increase the mass of the bulb, is there change of speed of the oscillation of the pendulum? When I decrease the mass of the bulb of the simple pendulum, is there increase of speed or decrease of speed of the oscillation? Okay, no, it's still the same. matter how I change the mass, increase or decrease the mass of the pendulum, of the bob. Now I'm going to change the length of the pendulum, okay, and make it shorter from this length. I'll make it shorter. Okay, the shorter the length of the pendulum, the faster it oscillates. So the faster it oscillates, the period is small. Now if I'm going to increase the length of the simple pendulum, the speed of oscillation is slow. If the speed of the oscillation is low, so it means the period is big. Okay, or it takes more time to move from from positive amplitude then negative amplitude, then go back to the positive amplitude. Okay, so let us see again if what will happen if I'll make the string shorter. So it oscillates faster, so takes small time to move one cycle. Compare when the pendulum is longer, so it takes long time to move one cycle. Okay, how about the acceleration due to gravity? If I'm going to increase the acceleration due to gravity, observe what will happen to the oscillation. It moves faster. But if I'm going to decrease, the acceleration due to gravity is smaller. Okay, as you can see, as I increase the acceleration due to gravity, then there is increase of speed of oscillation. So the greater the acceleration due to gravity, the smaller the period, or the smaller the acceleration due to gravity, the longer time it takes to move one cycle, or the bigger the period. So the restoring force F theta is tangential to the component of net force, right? And it's also tangential to the arc followed by the bob. So this is the restoring force, which is mg sin theta, and this is the arc followed by the bob, and that force, restoring force, is tangential to the arc, right? Tangential, it means it is perpendicular to the radius of the arc, and the radius of this arc is equivalent to the length of the string. Okay. Gravity provides the restoring force F theta, that's why there is mg, which is equivalent to the weight of the bob. The tension T, or the force acted by the string to the bob, merely acts to make the point mass move in an arc. Without the string, if the string does not act force to the bob, then the bob will go out to its arc path. Okay. Now, since F theta is proportional to sin theta and not theta, the motion is not simple harmonic motion. Okay. Simple pendulum is not simple harmonic motion since the restoring force is not proportional to its angular displacement, or its displacement. Rather, it is proportional to the sine of the angle. That's Hooke's law, right? The restoring force is proportional to the displacement of the object in simple harmonic motion. But in this case, simple harmonic motion, for simple pendulum, in this case, simple pendulum that is oscillating, we cannot say that the motion is simple harmonic motion since the restoring force is proportional to sin theta and not to the angular displacement theta. Now, but for very small angle, let's say 6 degrees, 4 degrees in radian, the sine of the angle theta is approximately equal to the angle itself in radian. So that's why the restoring force is equal to mg theta, since sin theta is theta, and which is equal to negative mg x, which is the arc path followed by the pendulum, over the length of the string, and that is mg over L. Mg over L can be compared to the spring constant if this one obeys Hooke's law, mg over L is the spring constant, and x is the displacement of the pendulum. So the restoring force is then proportional to the coordinate of the small displacement, and the force constant is K equals mg over L. Okay? Mg over L is equivalent to the spring constant. Because m, the mass of the bulb, the acceleration due to gravity, and L is the same at every position of the pendulum. And the angular frequency of a simple pendulum with very small amplitude, omega, equals the square root of the spring constant over m. And then spring constant is equivalent to mg over L, so we can cancel m. Then we have square root of g over L. This corresponding frequency and the period relationships are the frequency equals omega over 2 pi, since omega is 2 pi f. And then that is 1 over 2 pi over times g over L. And period is reciprocal to the frequency. So period here is 2 pi over angular frequency, and period is 1 over f. So we have 2 pi times the square root of L over g. Okay? So as you can see again, the object, the expression t equals 2 pi, which t is this period of the simple pendulum, which is equal to 2 pi times the square root of L over g. So as you can see in the expression, it does not involve a mass particle. So it means the period of the pendulum does not depend on the mass, but rather it depends on the length of the string. Okay? And also the acceleration due to gravity. So the period, the same length, the period of simple pendulum here in Earth is different when that simple pendulum is at the surface of Mars, or Jupiter, or any planet, which have those planets don't have the same acceleration due to gravity here on Earth. So the motion of a pendulum is only approximately simple harmonic motion. Approximately simple harmonic motion. Okay? Not totally simple harmonic motion. Approximately simple harmonic motion if the angle is very small. Okay? Less than 15 degrees. Okay? The angle should be less than 15 degrees, so that we can consider that as approximately simple harmonic motion, not totally. But when the angle is greater than, or a big angle like greater than 15 degrees, then we cannot consider a simple pendulum as simple harmonic motion, or that pendulum does not act in simple harmonic motion. So I have here a problem involving some simple pendulum. So the problem goes this way. First problem, a simple pendulum makes 120 complete oscillations in 3 minutes at location where g equals 9.8 meters per second squared. So we'll determine the period of the pendulum and its length. So given our cycles in 3 minutes, so what's the frequency? Frequency is the cycle per second. Okay, what's the number of cycles? 120 complete cycles over 3 minutes. 3 minutes is equivalent to 180 seconds. So the frequency, so 120 over 180 is 0.67. So that's the frequency, 0.67 per second. But we're not looking for the frequency, we're looking for the period. And period is 1 over f, reciprocal to the frequency. So period, I'll mark this as E. Okay, the period is 1 over the frequency, then that is 1.5 seconds. So you have the period. Next, what is the length of the simple pendulum? From the equation, t equals 2 pi, this is the period of the simple pendulum, times the square root of the length of the simple pendulum over the acceleration due to gravity. So we look for the equation of the length of the pendulum. So we have T squared equals 4 pi squared times L over G, or that is G T squared over 4 pi squared, which is equal to L, right? Or L, the length of the simple pendulum, is G, the acceleration due to gravity, times the square of the period over 4 pi squared. Okay, so the length of the pendulum L is G, the acceleration due to gravity is 9.8 meters per second squared, and the period is 1.5 seconds, and then this is squared over the 4 pi r squared, so this is 4 pi squared. So the length of the string is approximately 0.56 meters. Right. So this is the length of the string, length of the simple pendulum, and the period 1.5 seconds. So that's problem number 1. Okay, so let's proceed to sample problem 2. Using small pendulum of length 0.18 meters, physicist counts 83 complete swings. So from A to negative A, then back to A in 83 times in just 60 seconds or 1 minute over an unknown planet. So what is the value of G in this location? Alright, so let us obtain the equation of G. Period is 2 pi times the square root of the length of the pendulum over the acceleration due to gravity. It is dependent, the length of the string and the acceleration of the gravity. Okay, period is dependent on the length of the string or length of the pendulum and the acceleration due to gravity. We will look for the equation of the acceleration due to gravity. So we will square each side. Okay, so we have T squared equals 4 pi squared times L over G. Okay, so T squared over 4 pi squared will be L over G, or G over L equals 4 pi squared over T squared, or G equals 4 pi squared times the length over the square of the period. So we have the equation of G. Do you have the length of the string? Can we solve now? Do you have the length of the string? Yes. Do you have the period? No. So we need to look for the period first. The period, but what is given here is the cycle per 60 seconds, so that's the frequency. Let's solve for the frequency. 83 complete cycle over 60 seconds. Okay, so the frequency is 1.38 second per second. Okay, so it can move 1.38 cycle in 1 second. That's the frequency. So what's the period? T is 1 over F. So period here is 1 over 1.38 per second. Then period is 0.72 seconds. So we have the period. So can we now solve for G? We have L as the length of the pendulum and the period T. So G here equals 4 pi squared. Pi is approximately 3.1416 and length is 0.18 meters, okay, over the square of the the period. So the acceleration due to gravity, G, is approximately 13.71 meters per second squared. Okay, so this is the acceleration due to gravity at that certain planet, 13.71 meters per second squared.